Alright, Assalamualaikum and a very good day to everyone. So today we will continue our next lesson and next topic, which is regarding on the chapter 5 basic of filtering. So what basically that you will learn in this chapter, okay, you will learn about the type of filters and its applications, frequency response characteristic, filter circuit, first order filter and transfer function representations. Okay, so that is what we will cover in this lecture. Next, okay, in this slide, okay, the outline that we're going to look is introduction, types of filter, and what is frequency response. So, a little bit introduction about for this topic. So many networks behave or act as filter. In fact, you have know types of filter a little bit, okay, basic of filters in chapter 3. Okay, so we use filter to block or remove unwanted frequency components, and filter usually has been applied in many applications that need to retain components in given range of frequencies and discard the components in another range. So if you still remember, filter allows some frequency range to go through. For example, here, some frequency range to pass through, okay, in a pass band, and what it do with the rest of the frequency, it will filter out or it will discard. Okay, so this can be accomplished using electrical networks that call filters. Yeah, so we have passive filters network that is known as inductor, capacitor, and resistors, and we also have active filter network that is example of op-amp and also transistors. Okay, so let's recap what we have learned before in chapter 3. So we have learned about the frequency range over which the output is significantly attenuated. The one that is attenuated is in the range of the range is called in stop band. Okay, frequency that is inside the stop band will be filtered out or will be eliminated to pass through the filter. Okay, the frequency range over which there is a little attenuation is called as pass band, and there is also a cutoff frequency which is omega c. So cutoff frequency is defined as the boundary between the pass band and the stop band. Okay, so this is what we have learned actually in chapter 3. Alright, so now let's look what we have learned about filters in chapter 3 before. So we have low pass filter and we also have high pass filter. So low pass filter, it pass all frequencies from DC up to the upper cutoff frequency. So what is cutoff frequency? So this is the cutoff frequency. Okay, so this is the corner of the cutoff frequency. It usually lies in negative 3 dB. Alright, so low pass filter, it allows the frequency that is in a lower range to passing through the filter, and it will eliminate or it will discard frequency that is on upper frequency or higher frequency. Okay, whereas for high pass filter, it allows frequency that is higher frequency to pass through, okay, and it will eliminate or it will discard all the lower frequency. Okay, now let's look another types of filter, which is known as band pass filter and also band stop notch filter. Okay, I think these types of filter is quite new. We haven't discussed about this types of filter in our previous lecture. Okay, so now let's look what is band pass filter. So band pass filter, it allows some range of frequency. Okay, it contains a lower frequency and also higher frequency, a range of frequency that is between lower to higher frequency to pass through the filter. Okay, it pass a range of frequencies between omega C1 and omega C2. Okay, so pass band, right? So this is the range of frequency which is either low frequency and also there is high frequency to pass through. okay, that filter. Whereas for band stop ataupun also known as notch filter, okay, is a filters that will eliminate all signal within the stop band, okay, while passing all frequencies outside this band. So there are two range of frequencies, right? So pass band is between the lower frequency and also higher frequency. So frequency between lower frequency and higher frequency, it will lies in a stop band. Maksudnya it will not able to passing through the filters. Okay, so it is actually an opposite from a band pass filter. Okay, now let's look what is the filter response characteristic for low pass filter. Okay, so filter response for low pass filter. Okay, so this is the ideal low pass filter, which is it will pass through the lower frequency range and it will eliminate all the higher frequency range, and this is the cut off frequency. Okay, so ideal filter, it has like a block like this. Okay, the rectangular block like this. Okay, let me draw. Okay, so this rectangular block is for an ideal low pass filter. Okay, there is like a very clear separation between pass band and stop band. Whereas if the filter is a non-ideal filter, okay, non-ideal filter, there is like a slope here. You can see there is like a slope like this, okay, between the pass band and stop band. Okay, pass band is going to be straight line, and between the pass band and stop band there is a slope like this. Okay, and stop band, so it's going to be reduced. It will, because it is eliminated, or it will not allowed to pass through the circuit. Okay, so what is ideal filter? So ideal filter, all the pass band, okay, all the pass band area, the gain is 1. Okay, and for stop band, the gain is 0. Okay, meaning that we have a very definite value 1 and 0. 1 is allowed the frequency to pass through, 0 the frequency is not allowed to pass through. Okay, no transition. We said it is no transition band between pass band and stop band, because there is a very clear boundary between pass band and stop band. So that is for ideal filter. Whereas whereas for stop band, okay, so this is all the explanation, no transition. Okay, whereas for practical or non-ideal, also known as non-ideal, yeah, in real life it is very difficult to get an ideal filter. So practicality, we will have a non-ideal filter. So what is the difference between ideal filter and practical filter or non-ideal filter? So the difference is, for pass band, okay, at the pass band, any constant value, it has a very constant value in dB. Okay, it is not exactly 1, but the value usually is a constant value. Okay, so all that value will lies in a pass band. However, for a stop band, the gain is not definitely 0. It is very difficult to get 0 gain. There is a gain value, but the value is not 0. Okay, no absolute band stop. Okay, so there is a transition band exists. Okay, wait, yeah. Alright, so here, yeah, we can see, if you can see the graph here, the graph is start to decrease for the non-ideal. So meaning that there is no absolute band stop. It will not become 0, the gain, yeah. And for the transition, there is a transition band exists between the pass band and stop band. So what it mean by transition? So the slope here, yeah, there is a transition band exists between the pass band and stop band. So this is the filter response in ideal filter and practical filter for low pass filter. Alright. Okay, so now let's look for the high pass filter. So same goes with low pass filter. For an ideal high pass filter, there is a very clear separation between the pass band and stop band. So we know, yeah, for high pass filter, it allows higher order of frequency to passing through, and it will filter out or eliminate all the stop band frequency from passing through the filter or the circuit. Okay, so if it is a ideal filter, it has a very clear pass band, the gain is 1, and stop band, the gain is 0, and there is no transition. Okay, there is no transition. Okay, but for a practical usage, okay, it's very difficult to get an ideal filter. So for non-ideal, for the non-ideal, the pass band have a constant value. For the stop band, it is not equals to 0. Yeah, the gain is not equals to 0, and also there is a transition between the pass band and the stop band, right? Okay, so same goes with the band pass filter. So band pass filter, it allows some range of the frequency to pass through. So the range is between the lower range to higher range to pass through, and it will discard the rest of the frequency. So same goes for non-ideal, between pass band and stop band there is a transition, and for ideal filter, the pass band, the gain is equals to 1, whereas for non-ideal, the gain is constant in dB. Yeah, and for stop band, the gain for ideal filter is equals to 0. However, for non-ideal or impractical, the stop band area, the gain is not equals to 0. Okay. Alright, so now let's look what is a transfer function. So transfer function, also known as frequency response. So I believe frequency response, you all has familiar with our previous chapter, okay, where we have discussed what is frequency response. So frequency response or transfer function describes the relationship between the amplitudes and the phase angles of the input and output sinusoids, which are frequency dependent. So when we said about frequency dependent, so meaning that it will deal with the omega. Alright, so gain, how to measure a gain of a transfer function. So gain can be represented as H. Alright, so H j omega, okay, is equals to output of the amplitude divided with the input of the amplitude. Alright, so when we said about frequency dependence, so of course it's gonna relate with phase. Alright, so to know the phase, okay, the phase difference, so phase difference is represented as theta omega. So to know the phase difference, we're gonna be the output of the phase, okay, minus with the input of the phase. Alright, so now let's look what are the ratio of the phasor, okay, ratio of the phasor output voltage to the phasor input voltage as a function of frequency. So in our previous slide just now, we said that output H as j omega, right? H as j omega is equals to the output amplitude, okay, output amplitude divide with the input amplitude, right? So it also can be in terms of phasor. Okay, so phasor, it means that H in S domain. Okay, just now we are discussing H in omega domain. Now H also can be represented in S domain. So when it is dealing with S domain, it is actually dealing with the voltage. Instead of amplitude, it is actually a voltage. So voltage of the output divided with the voltage of the input. Alright, so please remember that H can be represented into two terms. One is in omega terms and another one in S terms. omega domain and S domain. Alright, so the magnitude of the transfer function shows how the amplitude of each frequency component is affected by the network, and phasor of the transfer function shows the phase of each frequency component is affected by the network. Alright. Okay, so next let's look example number 1. Find the transfer function of the network below given as Hs, okay, in meaning that we need to find in S domain, right? Is equals to V of V2, which is actually V at the capacitor, divided with V1, which is V from the source, right? Okay, so V at the capacitor we have learned in circuit analysis application in chapter 4, Laplace transform applications. So we know to find voltage at capacitor, so V2 is equals to 1 over SC, okay, multiply with IS, which is the current that flowing inside this network. Alright, so V1, what is V1? V1 is results of IS, okay, multiply with the impedance. Okay, so what is the impedance? The impedance is resistor plus with the capacitor, right? Total impedance we're gonna be resistor plus with the capacitor. Okay, in S domain, of course it should be in S domain because our H now, the one that we want to find is in S domain, right? So V1, okay, yeah, V2 is equals to 1 over SC, IS, I that flow, and divide with V1, so V1 is equals to IS multiply with the total impedance. So total impedance we're gonna be R plus 1 over SC. So we can cancel both of the IS. So HS is equals to 1 over SC divided with R plus 1 over SC. Okay, so we can simplify the equation. We will get as such. Okay, so now, since that we are dealing with S domain, so S domain, of course, if we can recall in our previous slide, they said there is also phase difference, right? Okay. So when there is a phase difference, as in phase difference, it will become S here is equals to sigma plus j omega. So what is sigma? Sigma is the material coefficient. Okay, so it will be changed with the states of the network. So here they said at steady state, usually sigma is equals to 0. So what is steady state here mean? Okay, the steady state here mean is the final value. Okay, steady state is equals to the final value. Okay, final value of a system approach. Okay, approach as time progresses towards infinity. Okay, so it is actually a final value of a system, okay, as time progress towards infinity after being subjected to an input or disturbance. Yeah, so it represents the long-term response. It actually represents the long-term response of a system. Okay, so usually at a steady state, the value of the coefficients or the sigma value is equals to 0, and since that it will equals to 0, so S will become equals to j omega. So what is omega? Omega is the value of the frequency. Okay, so therefore the magnitude and the angle of HS also can be calculated as shown below. Alright. Okay, now let's look another example that we have here. Example 2, given the transfer function of a network as HS is equals to S to the power 10 to the power of 4 and S squared plus 2000S plus 5 times 10 to the power of 6. And we need to evaluate transfer function at omega equals to 1000 radian per second and omega 3000 radian per second. So now let's look how to solve these questions. Okay, so first of all, okay, now have two value of omega. One is 1000 radian per second, and another one is omega equals to 3000 radian per second. And since that they didn't mention what are the states of the network, we assume that the state of the network is steady state. Okay, it is on a steady state, so meaning that your sigma is equals to 0, and therefore your S is straight away equals to j omega. Alright, so what we have to do now, just now we have Hs, right, equals to S 10 to the power of 4 divide with S cubic plus 2000 S plus 5 times 10 to the power of 6. So this is the questions, right? So we know already, we assume that the condition is in a steady state, so the sigma value is equals to 0. So therefore, S will gonna be equals to j omega. So what we have to do, we need to replace all the value of S equals to j omega. So we replace Hs now is equals to j omega 10 to the power of 4 divided with j omega squared plus 2000 j omega plus 5 times 10 to the power of 6. So now, since that the value of omega has been given to us, which is equals to 1000, so we just substitute inside this equation where the value of omega now is equals to 1000. So we solve this and we will get 10j over 4 plus j2. Alright, so we can convert we can convert this into another form, okay, into a polar form. Okay, so this is in a polar form. We can convert this into the radian and also degree. So you can just use your calculator, so you will get your answer, final answer as such, right? So that's not finished yet. We have another value of omega, where another value of omega is equals to 3000. So just replace the value of omega now in the same equation as 3000. Okay, and we can see the final answer that we get supposed to be as such, right? Alright, now let's look another example that we have here, example number 3. So in example number 3, they ask find the frequency response of the system shown below at frequency omega 1 is equals to 1000 pi, omega 2 3000 pi, omega 3 5000 pi, omega 4 7000 pi, and given the value of R is equals to 200 pi ohm and L is equals to 0.1 Henry. Okay, so first of all, we need to find the frequency response. So frequency response for a network, we know Hs is equals to V2 divided with V1. So V2 is a V at a resistor. So V at the resistor will be R multiplied with Is, and V1 is equals to the value of current Is, okay, multiply with the total impedance, where the total impedance is Ls plus R, right? So you can just substitute inside here. Total impedance is going to be Ls or SL plus R. So Is can be cancel each other. So the value, the transfer function equation will going to be R over R plus SL. So we already have the value of R. R is equals to 200 pi. Okay, R here is 200 pi plus L is equals to 1 over 0.1 S. Okay. So now from here, okay, we assume the condition is in a steady state as well. Okay, we just assume it is in a steady state, alright? And what we have to do, we need to find the value of the frequency response at the different frequency. So what we have to do, we have to convert we have to substitute S is equals to j omega. So therefore, H for j omega is equals to R plus all the S has to be replaced with j omega, yeah, j omega L. Okay. So we will get as such. This is our simplified equation. So what we have to do, we need to replace lah when omega is equals to 1000 pi. What are the value of h when 1000 pi j? So we just replace inside this equation 1 plus j 1000 pi L is equals to 1 over 0.1 over R. R is 200 pi. Okay, so I leave it to you guys to solve. Okay, so you just have to replace the value of omega with 1000 pi, 3000 pi, and 5000 pi, and 7000 pi. All right, so I think that's all. So we will see on the next lecture, part 2 for filtering. Right? Thank you.